Alright. So today y'all will be doing problem 1.10 from the book and 1.11. So 1.10 says for the function x of t is equal to 1 plus cosine 2 pi f naught of t, calculate a, the average value of x of t, b, the AC power of x of t, and c, the RMS value of x of t. Alright, so I'm going to go about this in a couple different ways, or just in one way really. It makes the most sense to me. But first, we'll write down our knowns. This is problem 1.10. So problem 1.10. So known. Our function, which we don't know is voltage or current, but it's just x of t, is 1 plus cosine 2 pi f naught of t. Correct. Just check to make sure. Yep. And they want us to find, so find average value, AC power, and they want us to find RMS value. Square. Alright, so first what we're going to do is, let's start with the average value. So we have a cosine, right? A cosine with a DC offset. This plus 1 adds a DC offset. So we have a sinusoid, it's AC, and we have a DC offset. So it's centered here on 1. Cosine of 0 is going to be 1, so when it gets added up plus 1, it's going to, now the peak is going to be 2. So it's going to be like this right here. Boop, and then over here, same thing. Alright, so you expect the average value of a sinusoid to be right in the middle, which here is going to be centered at 1. If it was just a regular cosine without any DC offset, then it'd be obviously at 0. But we can show it using math. So to find the average value of function, you do 1 over, we're going to use a period. We can't do the full integral from minus infinity to negative infinity because the bounds would give us an indefinite form. So we're going to take 1 period. So we're going to take t, and we're going to take integral of minus t over 2, positive t over 2 of 1 plus cosine of 2 pi f naught of t dt. And so we saw this integral to find the average value. So find average value. So essentially what we're doing is we're saying take the whole function, take all the area underneath the function, and then divide it by the distance of the area we found, and that gives us the average value. Same thing like a set of data, you add up all the values and divide it by the number of values in the set, and then you get the average. Same thing, you take up all the area, divide it by the distance in the area, and you get the average. And so here, what you do is just take the antiderivative, so it becomes still 1 over t on the outside, and then on the inside we have t is a constant, so it just becomes this constant times t, and then plus sine of 2 pi f naught of t divided by 2 pi from minus t over 2 to positive t over 2. And so what we get here, we end up with 1 over t, we're going to get a t over 2 minus negative t over 2, so that's positive t2 t, and then we're going to get a sine of 2 pi f naught of t, so 2 pi f naught of t divided by 2 over 2 pi f, this should be f here, I forgot the f, and then minus sine of minus 2 pi f naught of t over, t over 2, and then over here you're going to get 2 pi f. These are going to cancel one another, and so we end up with 1 over t, and then we have, a lot of my people I'm saying sine cancels. What I mean by that, not that they cancel, what I mean is when you have sine of 2 pi f, right, t, here for example, right, so let's say f is equal to 1 over t, right, and then you plug in t, right, for f. So you plug in, for a little case t, you're going to plug in, for example, t over 2, for example. So then this simplifies to sine 2 pi times 1 over t, because f is 1 over t, and then times t over 2, right? So these t's cancel, right? And these 2's cancel, and you're left with sine of pi. Well, sine of pi is equal to 0. And say, for example, this was sine of 4 pi, right? 4 pi 1 over t, t over 2, right? These t's would cancel. This 2 would make a 2 here, so you end up with sine of 2 pi. Put a 0. So when I'm saying cancel, like the signs cancel one another, I'm not really meaning they cancel because sine of, let me just be clear here, because the signs always get me messed up. This is where I always get messed up. This is equal, should be equal to 2 sine of x. So sines don't cancel. This is what we're doing in every integration. We're subtracting, and then we get a minus, a negative on the inside, and you combine these two, right, it's going to be 2 sine of x. That's not what I'm doing. When I'm canceling them, what I mean by that is because I'm getting a pi or an integer number of pi's, right? An integer number of any pi's is 0. The only way this is going to evaluate to 1 or some other values of pi over 2, or you have some angle that's in between, you know, pi over 2 and pi, or pi over 2 and pi, or pi over 2 and 2 pi, you know what I'm saying? So that's what I'm doing here when I say sine. I just want to interject and make that note so you guys aren't confused. These 2's cancel, and then you have t times, so you have t times 1 over t, these t's cancel, so you end up with 1. So the average value is 1, which is what we set up here, right? Wherever the horizontal that breaks the cosine directly in half, from the top part to the bottom part, this is going to be 1. Now, had this been 0, we would have had 0 here, then at the end we would have gotten 0, but it would DC offset, so the DC offset moved the average value to 1. So we found that. So now let's go ahead and, so we know the average value. We're going to put this here in the corner. We're going to put this in the corner here, so the average, we're going to actually put it here. Calculate the average value is 1. Now we want to find the AC power. So I'm not really sure what he meant by AC power. I've not heard people say it, but I think what he's talking about is the average power, the average normalized power here. And the reason I believe that is because power, so this we calculate the average value for x of t, right? And we're going to assume, x of t is a voltage or current source. And so what we did is we found the average value in that voltage or current source. Now we'll find the power. So power is usually I squared over R, I squared times R, or power can be V squared divided by R. Well, here we're normalizing it, so this R becomes 1. So then it turns into P can be either I squared or V squared. And so, assuming that x of t is the I or V, what we do is make this, we square this x of t, and now this will become our power. And so I think what the author wants us to do is calculate the average normalized power here, which the formula for that would be, we're going to do this from minus infinity, minus t over 2 to positive t over 2 times 1 over t x squared of t, where x is this, our 1 plus cosine 2 pi f naught of t. And the reason we squared it is because it was a current source or it was a voltage. And usually you calculate value, you calculate AC powered RMS for a voltage or current. That's why I made that assumption, because he gives a signal, he wants to calculate the power and the root mean square. Those are properties of a voltage or current source that are traditionally like used and analyzed in electrical engineering, circuit books or circuit analysis classes. And so we can make that assumption make that assumption pretty with good faith. We make that assumption with good faith. So here what we're going to do is we're going to take x squared of t. So we're going to do 1 over t times the integral from minus t over 2 to positive t over 2 of 1 plus cosine 2 pi f naught t, and then all of that squared in dt. So over here I want to just go ahead and write out the square of it. So the square of it is going to obviously be, we're going to have 1 plus a cosine squared of 2 pi f naught of t, and then we get a plus 2 cosine 2 pi f naught of t dt, right? So then we have to solve this, and so to solve this, it becomes 1 over t. This is going to be t here. This one is going to be, this is going to turn into 1/2 plus cosine of 4 pi f naught of t divided by 2. So then this becomes t over 2 for this part, and then for this part we're going to get sine. So we're going to get plus sine of 4 pi f naught of t divided by 8 here, 8 pi f naught. For this part, that's the antiderivative of that part. And then let me take the antiderivative of this. The antiderivative of this is sine 2 pi f naught, pi f naught on the bottom. There's 2's out front, so when we take the 2 pi f naught out front, the pi f naught will cancel, leave us just the 2. And then from minus t over 2 to positive t over 2. So what I'm going to do is I'm going to erase this part now, and I'm going to start solving this up here. So let's start solving this part right here. So this part right here, so we're going to get we'll leave 1 over t down here. We're going to come back to, we know this 1 over t is here, so we're going to get t half plus t over 4 plus sine of 4 pi f naught t over 2 divided by 8 pi f naught, and then plus sine of 2 pi f naught t over 2 divided by pi over f naught, and then minus t. So we're going to put this in. Let's put these in brackets here. So just think minus t over 2. And then over here we have minus t over 4. And we have plus sine of 4 pi f naught minus t over 2. And then over here we're going to get, 8 pi f naught, and then over here we're going to get plus sine 2 pi f naught yeah, so that's cool. So these are going to cancel. This is sine of 2 pi, of some multiple of 2 pi. So sine of 2 pi is 0, so these are going to go away. This one we have to be a little careful because this ends up being sine pi f naught, which is fine, but let's say this is sine pi, right? That'll give us 1, and we have minus sine of negative pi, which will give us negative 1. Add them together, we might get 2, so we might have to be careful about these two. I don't know if these will cancel one another, but let's deal with these t's first then. So let's do t minus t over, so that ends up being 2t over 2. And then over here we end up with t over 4 minus t over 4, so then we get plus t2 over 4. And what we end up getting here is we gotta make this bigger here, so we gotta make this part bigger. I think these sides are going to cancel one another out here. What we end up getting here is we end up getting, this is going to be 4t over 4 plus 2t over 4. And that ends up being 6t over 4, which is 3t over 4. Don't forget we had to multiply by this 1 over t. We forgot that. Let's multiply that back. It's going to be 3 over 2. 6 over 4 is 3 over 2. And then multiply by 1 over t, because we forgot the 1 over t, we just carrying it back up by the multiplication. These t's cancel, so then in the end we get 3 over 2. That's our AC power. That's our average AC power. So if this was like, for example, volts, it'd be volt squared, 3 over 2 volt squared, or something like watts, something in that ballpark. It'd be watts because you'd be volt squared times ohms. And so it'd be 3 over 2. The 3 over 2 is our final answer here for the average AC power. Or for the author calls it the AC power, but I'm calling it our average, average normalized power, because we made R equal 1 and then we squared it, things like that. Now, last thing is an RMS. Now, if you have a cosine, right? If you have a cosine function in this form, or a sinusoid, but sinusoid, sine, cosine, sine, if you change them, just lags 1/90 degrees. 2 pi f naught t plus a phase, whatever. If you have something, let's say a voltage signal in this form, then the RMS value is going to be a over root 2. Now, say you have a function where the cosine has been shifted, right, a DC offset for the voltage, then instead of having a root 2, let's say you have v over t. Let's say your v over t is a, right? Let's say it's some scalar like b plus a times cosine 2 pi f naught of t plus phi. Right? Okay, so then what you do is you go over to you want to graph this function. So for example, with our function, right? Boop, boop, boop. Right, this would be our example, this would be our A here. And this would be like this maximum height here would be, for example, this would be our B here. Right, this would be our B here. And so here what we get from the RMS, instead of having a over root 2, what you end up having is the square root. The RMS becomes the square root of it becomes the square root of not A and B here. Let me not put that here. This is a little bit confusing. Say for example you have B plus A, right? So put B here and put A. Well, there's this distance here, right? This distance here. Let's call this distance C in between B and A. So really you can do B minus A, right, for example. So then you end up getting B minus A, and you want to add that plus A divided by 2. So then what that becomes for our function, right? So in terms of our function, we have 1 plus 1 times cosine 2 pi f naught of t. Right? And so our distance, our difference between these two is c. C is going to be 1 because the amplitude of this function is 2. You see here it's 2, right? So for this example, our c here will equal to 1 because in between 2 and 1 is 1, and then our a here is going to be 1 as well. So with all of that in mind, now we just need to calculate the VRMS. The VRMS is going to be equal to 1, which is this horizontal, plus actually you take the average value. So the average value is 1 here, which is the horizontal that cuts the graph in half, and then you add it plus the distance to the highest peak. So the highest peak is going to be the distance from 1 to 2 is 1, and then divide that by 2. Now what you'll notice is we get 1 is the same thing as 2 over 2, and then you add that plus 1/2, right? So then you end up with 2 plus 1, that's 3 over root 2, and you end up with root 3 over root 2. What you'll notice is a root 2 factor times our AC power, which is how we know that we were on the right track here with the AC power. The RMS ends up being root 3 over root 2. And that's how you would go about solving this problem. With the communication, there are just different ways to approach it. Doing a communication method, you could consider this function as ergodic, and then you could apply a mean by computing a mean or computing variance to find the RMS or the AC power. But I just did a traditional circuits method because it makes it a little bit more easier to kind of take in and handle it, versus if you do it with a traditional, like, let's compute the mean, let's compute the variance. This makes more sense in my head, so that's the way I went about doing it. That's all for that problem. Let's move on to problem 1.11.